today I will talk about the spatial network calculus and the performance guarantees in wireless networks. So the title is in reference to network calculus, which is the presentation that we just heard. So I will this is joint work with Professor François Baccelli, who is also here. I will skip this very gentle introduction on network calculus, given that our memories are probably still fresh. And the problem that we're interested in is really in the spatial domain. So I start with the motivation of the problem. Given a very large wireless network, arbitrarily large, potentially infinite, what is the performance guarantee that we can give on all links? So I illustrate the problem by this figure. This is a device-to-device network where you have pairwise transmitter and receivers. In this example, we assume that there is a fixed distance between every pair of transmitter and receiver. And you can see that assume that you are the receiver at the origin here. You receive signal from your dedicated transmitter, but also you receive all the interference from the rest active transmitters in the network. And also you experience fading due to the nature of a wireless medium. Another thing is, if you move from this link to another link, you observe a different network geometry. So the question really is, how can we guarantee something for all the links, despite their geometry is different? And this is in the context of characterizing the worst case performance in wireless networks in the spatial domain. Also relevant to user experience and ultra reliable and low latency communication. So to consider this spatial domain problem, we need spatial modeling, and the stochastic geometry rises up as this theoretical tool that has been very effective in the past few decades. And the reason is that it is effective in modeling the randomness of known locations, and also it allows to derive provable performance on the in terms of the spatial aspect. So the first category of the result comes from spatial average analysis. So it is known as notion of the typical user, where you observe the network and you take the average over all links. So you get the spatial average. And there is more than 1,000 papers on this category. It is particularly effective thanks to the tractability of Poisson type models. And in the second category is this link percentage characterization using stochastic geometry. And this line of work is proposed because obviously because the lack of fine granularity of spatial averages, because you would not know what is the percentage of users or links in the network that achieve certain target performance. So for us, we push this question to its furthest form. We ask the question which is, what is the performance we can guarantee for all links in arbitrarily large wireless networks? I make this analogy and comparison between classical network calculus and the spatial network calculus. Network calculus was developed for deterministic bounds in queuing systems, and it is about the delay or system backlog that is at all time of the system. And in contrast, the spatial network calculus targets at every wireless link in space. So there are some similarities in the sense that they both target performance guarantees, and they all both rely on the notion of regulations, which I will introduce the spatial regulation in a moment. But there are also some key differences. For instance, the performance metric that are interested is in network calculus is the delay and backlog of the system, and in spatial wireless network calculus, we care about the signal to interference and noise ratio, which is the key to determining the wireless service curve. And also in terms of the analytical tools we use to get to the guarantees. And finally, there's also a different a notion of strong versus weak regulation in the spatial network calculus, which I will talk about in a moment. And I will start with the strong regulations. So my first definition is called ball regulation, and it says that a stationary point process is strongly sigma rho mu ball regulated if for all radius, the number of points within this radius is upper bounded by the polynomial formula on the right. So what I mean is, if you center at the origin and you take a radius and you count how many points are located within this ball. And this is required for all radius. By the assumption of stationarity, the same bound extends to when you are centered from an arbitrary location in space. And furthermore, we could prove that, in fact, for all the location in space, jointly they are almost surely upper bounded by the polynomial form. We could also generalize this sigma rho nu ball regulation to a general form ball regulation, where we only need to only require that on the formula on the right hand side of the inequality increases squarely. And the remark is we could easily come up with the notion of ball regulation for a deterministic framework, where we will require this condition to hold for the location in space. Now I will give a few, in fact, one counter example to ball regulation and one example to ball regulation. So the counter example is the Poisson point process, which is widely used in modeling spatial aspects of wireless networks. It is known that the number of points in any in this case is the ball radius r. It is proportional. The mean is proportional to the size, and it is Poisson distributed, so it cannot be almost surely upper bounded or lower bounded. So it is not ball regulated. And the second example is a hardcore point process where there is a minimum distance specified between any pair of points. So using basis packing, we can prove that indeed we can find this polynomial form bound on the number of points for all radius r, and it depends the parameters depend on the minimum distance h. One can regulate a Poisson point process by removing a small subset of points and making it hardcore. My second definition is called short noise regulation. And it says that a stationary point process is strongly sigma rho nu short noise regulated if for all non-negative bounded and non-increasing function and for all r, this inequality holds true almost surely. So what is on the left-hand side of this inequality? This is you are taking into account of all the points within the ball of radius r, and each of them generates a shot to the origin. In fact, here is x minus 0 because we're looking at origin. So you look at origin and you sum up all the shots from the points within certain radius. And it is upper bounded by the this integral form that depends on the this function L. So first observation, if we take this function L to be 1, then we retrieve the definition that we just mentioned, which is sigma rho nu for regulation. And the second point explains why we call this short noise regulation, because if we take this radius arbitrarily large to infinity, then we obtain an upper bound on the short noise, which is the summation of all the points in the point process, and you sum up all the shot power from each of them. And it is upper bounded by this quantity that we denote by A sub L, because it depends on the form of L in its integral form. In fact, we could prove a stronger result, that is the ball regulation is equivalent to short noise regulation. And the proof relies on summation by parts and the Riemann-Dilthey integral. So we could further show that the ball regulation is really needed, it's a necessary condition if we want bounded short noise everywhere. And the second thing to notice is in the definition of short noise regulation, we have a very loose condition on this function L. And the universality of the function L is useful in deriving bounds other than the short noise regulation, which is illustrated by the following example. We consider a stationary point process, but each point is also marked with independent mark. And now the short noise really is changed into the summation of all the points, and each of them is equipped with a mark hx, and then this shot lx. Use the short noise regulation, we can prove that if these marks are non-negative with finite mean, and they satisfy the Kaimat condition, if in addition the point process is strongly sigma rho nu ball regulated, then we can derive a tail bounds on the Laplace transform of the short noise conditioned on the point process phi. So this condition means that the tail holds for all the location in the plane. And the reason we define this regulation is, in fact, we are, as I mentioned before, we're interested in the metric of signal to interference plus noise ratio. And the short noise in a form represents the amount of interference that you observe in the network. So eventually this result will give us the tail distribution of interference and eventually on wireless service curves. So I defined the two regulations, Bohr regulations and short noise regulations, which are equivalent. The second class of regulation I defined is called void regulation. And it says like that a stationary point process is strongly Tor void regulated if from the origin and a closed ball of radius tau, I observe at least one point from the point process. Again, by stationarity, this holds everywhere in space, and they hold true jointly. The reason we define this is relevant to the notion of coverage, for instance, in cellular and satellite networks. And there are a few properties that I would like to mention about the regulations that we've introduced. The first property is the superposition property. It says that if I have a class of stationary point processes, and if each of them is strongly sigma rho nu Bohr regulated, sigma I rho I mu I, then their superposition is also sigma rho nu regulated by the sum of their parameters. An example is the superposition of hardcore point processes, which means that being hardcore isn't really necessary to being Bohr regulated or short noise regulated. And it has applications in heterogeneous cellular networks and overlaid networks. The second property I would like to mention is the displacement property. It says that if the point process is originally strongly Bohr regulated, then after a random displacement, which is bounded and also stationarity preserving, then the resulting point process is again strongly Bohr regulated. And the same goes for void regulation. So up to now, I introduced strong regulations, and now I clarify the difference between strong regulation and weak regulation. And I will give the definition of weak regulation in the next slide. The reason we define weak regulation is we are interested in the perspective of a subset of observers in the network rather than the entire space in some cases. For example, when there are two set of transceivers, a set of primary transceivers and a set of secondary transceivers, for instance, in the concrete example of cognitive radio, we are interested in the performance of perhaps the primary set of transceivers, and they require different performance targets than the secondary transceivers. And another example is when there are a coexistence of multiple systems that may employ different power transmission and different distribution of points. We would like to be able to characterize each individual network's performance. The notion of weak spatial regulation is built upon Palm calculus. So let phi and psi be two stationary point processes. They're jointly stationary and ergodic. I say that phi is G-ball regulated with respect to psi if for all radius. When I observe the number of points within radius R, the number of points is upper bounded by this G function. And now we're really looking at a point that belongs to the observer point process psi. We can prove that strong regulations imply weak regulations, and the converse is not true in general. And there are two examples. If we take any stationary point process, they are void regulated with respect to themselves for any arbitrary tau larger than 0. And if the 2 point processes phi and psi are independent, then the notion of strong and the weak are equivalent. So I introduced two classes of regulation, the first class being ball regulation and short noise regulation. And the target of this regulation is to control the clustering of points in the network in order to control interference. And the second class is the void regulation, which aims to control coverage or signal power. I look at the concrete example of the device-to-device network again. This is the figure that I showed in the first few slides. So there are pairwise transmitter and receivers. They are distance tall apart, and by the definition, we immediately know that the transmitter point process is tau void regulated with respect to the receiver point process, because when you are centered at any receiver, it always observes at least one transmitter within this distance tau. And we look at the typical receiver at origin. We use this h of x again to denote ID small scale feeding. And now this function L represents the path law from path law function. So if you take the transmitter and the receiver pair, and the path loss is a function of the distance between them. And the SINR is the ratio between the signal power, which is the fading from the desired transmitter, and the path loss with distance tau in this case, and the amount of interference it receives from all the rest of the active transmitters in the network plus noise power. We're interested in this quantity called link reliability, which is when we fix the geometry. For instance, we fix the entire realization of the point process, and we look at the point receiver at the origin. We ask, what is the chance that under small scale fading, this link achieves a success probability with respect to some transmission threshold data. And based on previous results, we prove that if the point process, the transmitter point process is sigma rho nu ball regulated with respect to the receivers, and the fading statistics are chimer, then for any transmission threshold, the reliability is lower bounded by a deterministic function. And the way we obtain this result is through previously this stochastic tail bound on all links using short noise regulation. So on the right-hand side, I plot the figure of realization of a device-to-device network, and the blue curve is the simulated result for the minimum reliability for all links in the network. And there are two, this red curve and the black curve are obtained by using this zeta theta function that we obtained. And one thing to notice is that zeta of theta goes to 1 as theta goes to 0. It means that there exists some small enough transmission threshold such that we can guarantee arbitrarily large reliability for all links. And what this almost surely true condition really means is that we look at the entire network, and for all receivers, their reliability is lower bounded. So this is exactly the goal that we have at the beginning of the talk. And now there is an interesting intersection between the classical network calculus and the spatial network calculus that we just proposed. Now the goal is we could combine the two regulations in time and space to guarantee something for all packet arrivals for all links in wireless queuing systems. Again, I take this device-to-device network case, and now I put some, I model the temporal traffic of each link at the transmitter, and they try to send the packets to the dedicated receiver, which goes through the fading and the interference, and the service rate is dependent on the signal to interference plus noise ratio. And combining the results from network calculus and spatial network calculus, in the absence of fading, and if in addition at each queue it is upper constrained, in fact by some arrival curve, then the latency at all queues in the entire network is upper bounded. If we consider climate and ergodic fading and the stochastically bounded arrivals, then the tail distribution of latency at all queues are bounded. It is well known that if the point process is not well regulated, for instance, in the case of Poisson point process, then there is always a non-zero fraction of unstable queues in the network. Two other network architecture I'll briefly mention is ad hoc networks, where each transceiver tries to establish link with some nearby transceivers, and thanks to the spatial regulation, we could prove that there exists always a path between any transceiver to another transceiver, and every link in the path has a link reliability that is lower bounded by a deterministic function. So we could further apply the concatenation of queues with each with the same lower bounded service curves. And in the case of cellular network, where we have a bunch of base stations in the network, and we also have users distributed in every cell of the network, we have two-point processes, the validation point process and the user point process. And the spatial regulation required is slightly adjusted such that in addition to guaranteeing the signal to interference plus noise ratio, we also need to guarantee that the number of users per cell is upper bounded. To summarize, we propose a spatial network calculus for performance guarantees in wireless networks. And instead of focusing on spatial averages, we are interested in the performance for all links, which are of stochastic nature in the presence of fading and of deterministic nature without fading. Some open questions, including the tightness of the bounds that we derived, as we have shown that we exploit inequalities in several steps. And the second open question is about modeling mobility and their respective bounds we can derive for the entire network, and also the algorithm implementation of the regulations that we defined. Thank you.